Welcome back, everyone, to the eCoreAcademy e-learning platform. Today, my name is AJay, back with yet another geometry video for you all. Today's lesson topic, if you didn't already see in the thumbnail down below, it's the bisectors of a triangle circumcenter. I know this might seem a bit confusing. We're just going to be building up off of triangles, as I like to move forward by looking at polygons with the least amount of complexity, or not necessarily complexity, but least amount of side lengths and angle measurements, to higher level regular polygons that go up to, nonagons, pentagons, all past that, going in that stage, dodecagons, things like that. We're going to be looking at those relationships later on. But right now, I want to dissect the basic shapes, starting with triangles, moving on to quadrilaterals, and we'll be moving on so on and so forth. So I'm going to be looking at triangles, and we're going to be looking at a specific property of triangles, something that's not often looked at in triangles. Something that's not very commonly looked at in triangles. So we're going to be looking at the circumcenter, and it's going to actually have to do with triangles and actually circumscribing triangles. And I'll show you exactly what that is. But before we jump into today's lesson, please make sure to smash that subscribe button down below. Hit that like button on this video, as well as turning on post notifications by hitting that bell underneath the subscribe button to get notified on any of our channel's latest posts at eCoreAcademy. All three of those things are very greatly appreciated and will only help you. So, as I was saying, today's topic is bisectors of a triangle circumcenter, and the whole theme and purpose of today's lesson is to discover what are the bisectors of a triangle and in what manner do they create the circumcenter, and exactly what does the circumcenter do, what are some of its properties, and what does it mean to actually circumscribe a triangle. So we're going to be looking at triangle and a very unique property that it has. So let's jump right into it. So let's look at concurrency first. Concurrency is very important in order to open up our topic here of bisectors. So in order to understand bisectors and how they create the circumcenter, the whole process of today's lesson, we're going to be looking at a basic fundamental process called concurrency. So let's look at the concepts of concurrency. So in order to be concurrent, it's when three or more lines, rays, or line segments intersect at a common point. So that's when three lines, rays, or line segments, they all have a common point of intersection, and that point has to do with the circumcenter, of course. So, and in order to be concurrent, in this case, you would only need two lines in order to identify where this point of concurrency, or this concurrency, would occur in this case, because we're only looking at an outlook that affects the triangle itself. Technically, you would not have lines that would be intersecting more than once at any given time. That's not possible unless they were on top of each other. So you'd only need two lines to actually show this. But in order for concurrency to occur, and with the specific property in this lesson, you need to know that it's three line segments intersecting at one common point in order for all three lines to be concurrent. And of course, the point of concurrency is the point at which three or more line segments intersect. So after you figure out that you have three concurrent line segments, they'll intersect at a common point. This common point of concurrency is the point of concurrency, where these line segments intersect. So I'll show you a little example here, very simple. If we have a line here, a line here, and a line here, we'll name these lines let's keep this as line segments. So I'll draw these out as line segments. So we have line A here, line B, and line C. As you can see, they all intersect at a common point, and there are concurrent lines. So equals concurrent lines. And because of that, we know that it will have a common point of concurrency, which is basically the point of intersection. I'm just eyeballing that right now, but if you're given it on a coordinate plane, you can of course get an exact measurement of where that point of concurrency would be located. All right, so let's move into our lesson for today. So let's look at circumcenters and bisection, the whole topic of today's lesson, the whole purpose, what we're trying to discover. So let's look at perpendicular bisectors and how exactly they can create the circumcenter. So a perpendicular bisector is a line that is at the midpoint of and perpendicular to a line segment. So a perpendicular bisector, I've already shown you what this is previously, but it is a line that is basically at the midpoint of a line segment. So what it does is it intersects a line segment and splits it into two equivalent halves. And when it intersects that line segment, it's going to intersect it at a 90-degree angle, making it perpendicular. And then, of course, you have your circumcenter. So it's the point at which the perpendicular bisectors of each side of a triangle meet/intersect. So there are three sides of a triangle. And if you're going to have separate perpendicular bisectors for each and every side of that triangle given, you're going to have three different perpendicular bisectors. And when those bisectors are actually going to intersect the triangle, they're going to at one point intersect each other. All three of them are going to intersect at one common point. And we know that if they all intersect at a common point, they must be concurrent lines. So perpendicular bisectors of all sides of a triangle are going to be are going to be concurrent, making them intersect at a common point called the circumcenter. So that's the point of concurrency for the perpendicular bisectors in a triangle. So what that basically looks like is if I were to draw an equilateral triangle here, simplest way of showing you that. So we'll say that this is equilateral. Write that here. Equilateral. So if we know that this is equilateral, what we're going to do is we're going to draw the perpendicular bisector, a line that will intersect, excuse me, a line that will intersect each side of the triangle at a 90-degree angle and split it into two equal halves. So let's assume that this is one perpendicular bisector intersects at a 90-degree angle, another one 90 degrees, and another one, splitting all sides into equivalent halves. So these three angles will obviously meet up in the center at this common point of this acute triangle, this acute equilateral triangle, and that is the circumcenter. Very simple concept. And just to give a little overview here, if you're looking at a perpendicular bisector, it's when you're given a line. Assume that this is a side of a triangle. That line will intersect this line given here, in such a manner that these two sides will be equivalent, meaning this side will be equivalent to this side. Both are two halves of this entire side of the triangle, and it will intersect at a 90-degree angle in order to actually do so. So that's a perpendicular bisector, basically magnified of what's happening here in this process of creating our circumcenter for this equilateral triangle. So circumcenters and bisection part 2. Let's look at the location of the circumcenter. Let's look at specific scenarios, and it has to always do with angles. Like I said in my previous video, angle measurement can always be used to identify it automatically implies side length classification. So all you need to do is deal with your angles given. So let's look at the location of the circumcenter. So in an acute triangle, a circumcenter will lie inside of the triangle. Like I showed you before, in an equilateral triangle, it will always lie inside because it's an acute triangle. So the circumcenter will always lie inside of the triangle if it's an acute triangle. If it's a right triangle, the circumcenter lies on the triangle, so on one of the side lengths of the triangle if it's a right triangle. And then, of course, for an obtuse triangle, the circumcenter lies on the outside of the triangle, meaning on the exterior of all of the sides. So I'll give you an example here. So for your acute triangle, you're going to have, I'll use the same example with the equilateral triangle here. When you have all of your bisectors drawn, you can tell that this point of the circumcenter is in the center. Write that here. And it's inside. And then for your right triangle here, indicated with the right angle, you're going to intersect it here. One goes here. One line goes there. Another line will go here, going across, splitting this line in half. So that'll go here, 90 degrees. And finally, you'll split this side in half as well. So that'll go 90 degrees. And they'll all intersect on one common point. Most of the time, it's going to be on the hypotenuse. So that's on the triangle for right triangle. So that's on. And then, of course, your obtuse triangle right here. It'll split the actual figure in such a manner that the circumcenter will be located on the exterior. So you'll extend these line segments outwards, just as shown here. You'll split it up across as well. So intersecting here, over here, and of course here as well. So that is your circumcenter on the outside, so outside here. I encourage you to try that yourself. Try and prove that in its own capabilities. Use actually find out the side lengths of these triangles as well, on top of just the angles, and try and prove that yourself. But this will always be true in any case. So circumcenters and bisection part 3. Let's look at actually what an extended point of not just the circumcenter, what exactly the circumcenter can actually do for a triangle. So let's look at the term circumscribed, deriving the same exact prefix. So when using a compass in the circumcenter given, you can connect all of the vertices to construct a circle that circumscribes a triangle. And what circumscribed means is encircling and touching each vertex of another figure. And this circle, I said Z circle, meaning this is often referred to in geometry, the Z circle. Z circle is basically like your, you could say it as your like your governor circle, your representative circle. So the Z circle is circumscribed about a triangle if each vertex of a triangle lies on the circle. So on Z circle, sorry, that should say on Z circle, on Z circle. So basically, what that's saying is, if you can create the circumscribe a triangle, you're basically placing the triangle inside the circle so that each vertex is a point on that circle. So I'll show you what that looks like. If you're given another equilateral triangle here, and you've already done all the bisectors of this triangle, calculated them, and then you found out that the circumcenter of this triangle here is in the center of this triangle as shown. So what you're going to do is you can all you're going to do is you're going to put one of your compass points on that center, or what you can do is you can merely use a ruler to calculate the distance and keep that constant radius and use geometric software. But you can use a compass, place your point here, and put it in on the one of your vertices, and you're just going to draw around it entirely until you form a circle. And this circle has 3 points that are all points vertices of the triangle, and that's going to be circumscribed. And there are different relationships with that. You can tell that the side lengths of the triangle, some can be represented, if it's a right triangle, as the diameter, and so forth. And I'll show you how exactly that's going to be created. There's different types of methods, and this has to go with the orthocenter and the circumcenter, as well as the centroid of triangles, which is one of my later videos coming up. So yeah, this is how you create a circumscribed, this is how you circumscribe a triangle. You're connecting all of its vertices, and all of those vertices will be on a point that basically encompasses this triangle using these circumcenters. So I'll indicate that circumcenter is very important. So this is more like a 3-step process if you think about it. Very simple. I'm just breaking down 3 steps of this process, starting with your perpendicular bisector, finding your perpendicular bisectors, using them to calculate the common point of concurrency of those 3 lines, which is, of course, your circumcenter, and then using your circumcenter and a compass to merely create a circumscribed circle around your given triangle. Circumcenters and bisection part 4. Let's look at the Pythagorean and circumcenter theorem. So after you actually circumscribe a triangle, you can actually use the Pythagorean theorem to calculate the area of that triangle, given if you do not know the side lengths given. So the circumcenter theorem states that the circumcenter of a triangle is equidistant from the vertices of the triangle. So if we look back here to my previous slide, this circumcenter will have an equal distance to all points. So it's basically the center of this triangle, of this circle. So it'll be equal distant from all points of the circle as shown. And so that's what it means by equidistant in all possibilities. And then the Pythagorean theorem states that a squared plus b squared equals c squared. Very common. It has to do with a right triangle. So if you're given an example in which you have to relate to a circumscribed triangle, I'll still continue with my oh, sorry about that. I'll continue with my equilateral triangle example, trying to keep it consistent. So here we have our equilateral triangle, and we have our circumcenter here, and we have our circumscribed circle of this triangle here. So we have a circumscribed circle here. And what you can do is you can actually use the Pythagorean theorem now. Since you know that the point of concurrency here is going to be equidistant from all sides, you can split this triangle up using your perpendicular bisectors as shown that intersect at the center here. And you can basically just draw them out to redraw, keep your perpendicular bisectors here that intersect at 90-degree angles. And you can split this triangle up into 3 different right triangles as shown if you don't know the area of this equilateral triangle, or you don't know any of the dimensions of this equilateral triangle. As you can see here, it splits it up into 6 different right triangles if you look closely, and you can use the Pythagorean theorem given the radius of this circle here, or the distance between the circumcenter and a point on the circle, or any of the vertices in general. So you can utilize this for all six possible right triangles. And of course, this only applies to right triangles. The Pythagorean theorem is only meant for right triangles, and that's saying that it's just saying that the hypotenuse of C is equivalent to a squared plus b squared, as well as the square of itself. So the other 2 side lengths squared together, the sum of their squares equals the square of the hypotenuse. So as simple as that. All right, everyone, that's been the eCoreAcademy e-learning platform, and that's the end of today's video. I hope you all enjoyed. Please make sure to like and subscribe down below and turn on post notifications to get notified on any of our channel's latest posts. Make sure to visit our website at www.ecoreacademy.org. We have full unlocked access, a lot of perks and extra bonuses aside from all of our social media platforms and our YouTube channel. There we give you full unlocked access to what we offer as an educational platform. So educational online platform, and there we have unlocked access, full unlocked access to organized course studies that go along with integrated worksheets, quizzes, and note sheets that go along with each and every single video, organized into lesson format. And all of our videos shown here on YouTube are going to be there as well, accessible. We have our contact information, event information, and many other perks and tricks there as well. So please make sure to check that out. All you need to do is make an account there for free, completely free. Also, you can email us at eCoreAcademy@gmail.com. As I said before, all of our information to contact us is on our website as well as our address items as such. But our email is always open at eCoreAcademy@gmail.com if you just want to reach out or ask us any questions. And finally, please visit all of our socials in the description box down below at Facebook, Twitter, and Instagram. We have our links there. Please check us a follow out there, see what kind of interesting content we have, and use that medium to share it to anyone else that might find these videos helpful or just interesting in general. Once again, everyone, I hope you all enjoyed this video. I sure had a blast making it. This has been AJ, and I will see you all in the next one. Peace.